Assalamu alaikum warahmatullahi wabarakatuh. Dear students, this is actually our last recording for lecture number 16 that actually talking about the XOR and XNOR. This will be part number 3 for that lecture, and this will be the last part of the lecture and also the last lecture in chapter 3. So, as we in the previous recording, we have talked about the XOR and XNOR, and we have shown an example how can I use and utilize the XOR and XNOR. We want to continue with this lecture talking about the 3 input NOR, and also we want to demonstrate the TT and the K-map for both 2 input and 3 input XOR gates. So, this lesson will be about the TT, the truth table, and K map for the XOR and the XNOR. In the last lecture, we have actually shown the gate symbol, the equation, and the truth table for the XOR and the XNOR. And we, in order to solve the problems with XOR and XNOR, we can replace the XOR and the XNOR with we decompose them through the TT, through our knowledge of the sum of mean terms and product of max term, SOM and SOP. So we can derive alternative equations for the XOR and XNOR. This translation or transformation has an advantage and a disadvantage. The advantage of using the gate of the XOR as it is definitely clear for everybody, because right now I can implement a 2-level XOR as only one gate. If I have here X, Y, and Z, so if I have Z equals to X or Y, okay, this means I actually have done this or implement this function with the 1 tau delay using one gate. Okay. Type. What if I implement the same function using the equations that we have mentioned, using the sum of min terms and product of max terms? Advantage is that right now I have the function in standard format, so I can easily manipulate the equation on the Boolean algebra level. However, there is something that I'm paying for this, okay? Nothing comes for free, okay? If I do this transformation, okay, let's see what will be the implementation of the circuit through those equations. So if I take that SOM, sum of min terms for the XOR, that means I have to implement this. So right now, Z will be equals to as we mentioned, X bar, Y, or X, Y bar. If I implemented this function, that means I have to have 2 AND gates. The first one has input X bar, Y. The second one has inputs X, Y bar. And both are connected through an OR gate to give me the function Z. Now, which of those implementations you will go for? for this. This is standard, SOP standard. So automatically the delay of the circuit is 2 tau, and the number of gates are 3 gates. This is a whole big circuit, while here I only used 1 gate with 1 tau delay and 1 gate to implement the same thing. And this is the advantage of the XOR, okay, as a gate. So if you ever have this scenario that you are looking for, you better go to the XOR as a 1 gate. So maybe you ask yourself, why we learn this? To manipulate any function. Because if this is part, if Z is only part of a circuit, and you want to manipulate this circuit, you need to work with Boolean algebra, you want to put it onto stable, you need to manipulate it using K-map, okay? You have to convert it to its original or standard SOP implementation. Right. Maybe some of you come and ask me and tell me that why we are using SOM for the implementation of the XOR. Why don't we just take the XOR from the two stable and put it on K-map and simplify it? Maybe we get a format for the equation better than the SOM. The SOM by definition is the biggest circuit with maybe the best delay, but maybe I can simplify the circuit more. So let's try to do that. So can we build the K-map for the two variable or input XOR? By the way, anything we are describing and mentioning for the XOR also exactly replicated and valid for the XNOR. Okay, so can I build the K-map? Yes. K-map looks like this. Two variable, and I have here X bar X, Y bar Y. From the two stable, can I put it on K-map? Yes. So I know the location of zeros. So 0, 1, 1, 0 from the TT. Now, can we simplify this? Let's try to simplify. Rules of simplification. I need the minimum SOP for the XOR. Can you go to the left, to the right? Can you group this one with any other one? No, because it's surrounded with zeros. So actually the equation that you will get is this term alone, X bar Y. Next, this one, left, right, up, down. There is no simplification that the K-map can provide to me whatsoever. So accordingly, the equation for the second term will be X, Y bar. Now, going to the essentiality. Is the first one essential? Yes, it is essential. Second one essential? Yes, it is essential. No other contours cover this one. So accordingly, the equation that you will get for the output will be identical to this. There is no simplification I can do for the XOR by itself. However, if the XOR is just part of another circuit, I may be able to simplify, as the example that we have discussed in the last lecture. So in the last lecture example, you can go and simplify the function that we have in the example. But for the XOR by itself, there is no simplification. This is the simplest, so it's one of two things. Either put it as an XOR or put its equivalent. Now, the last thing that we need to mention about the XOR and XNOR is the 3 variable XOR and XNOR. I can have an XOR with 2 inputs, or 3 inputs, or 4 inputs, or any number of inputs. Okay, we need to learn a technique which is easy for us to build the truth table for the XOR. So if I'm having a 3-variable XOR, how the XOR will look like? Will look like this: X, Y, Z, and here I have function F. Can I build the truth table for the 3 input? Definitely fine. Representing this as an equation, so the equation will be X, XOR Y, XOR Z. Okay? How the TT for this will look like? If you have the same operator between more than one literal or term, you can use the properties. So I can associate. So there are many ways for me to drive the truth table for 3-variable XOR. First of all, we want to build this TT. I have here 3 inputs. X, Y, and Z. I have here the designator, as we agreed. And these are the inputs. And I want to drive F, the output. Okay? First of all, how many rows do I have? 3 inputs means 2 to the power 3 means I have 8 different rows. Can I fill in the TT? Yes, for sure. 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. Designator is 0, 1, 2, 3, 4, 5, 6, and 7. None of this information is new. We already learned how to do that even from chapter 2. But right now I want to drive an equation for F. Okay, so there are 2 methods to do that. I can do it baby steps. So I can call X XOR Y, I can call this W as an intermediate. So can I drive? Let's do it with another color. So F is actually the result of XORing between X and Y, and the result could be XORed with Z. So we can take this and call it W. Can I get an equation for W? The answer is yes. Can I put W on TT? The answer is yes, for sure. So here I can have W. What's W? W is the result of XORing between X and Y. And I already learned and know the TT for the XOR. So accordingly, can I XOR X with Y? For sure. 0 XOR 0, 0 XOR 0 from the TT is 0. 0, 1, 1, 1, 1, and then 0, 0. This is the XOR between an X and Y. Then I need to drive what? Drive the column for F. If F is the result of XORing between W and Z, can I XOR? Yes, I remember. 0 XOR 0 is 0. 1 XOR 0 is 1. 0 XOR 1 is 1. 1 XOR 1 is 0. Again, 0 XOR 1 is 1. 1 XOR 1 is 0. 0 XOR 0 is 0. 1 XOR 0 is 1. What I drive here is the truth table for F, which is the output of a 3-input XOR. Okay? There is a trick here that you can use in order to drive F without going into all of this hassle. And this trick comes from the fundamental definition of XOR. Remember, XOR is either me or you, but not both of us. This is how we explain the XOR as a function. However, XOR can also be viewed as some other explanation. The XOR is actually recognize the odd number of ones between the inputs. Recognize the odd number of ones between the inputs. And this is clear here. So if I have the number of ones even, means the XOR is 0. If I have the number of ones in the inputs odd, means XOR will be 1. Can we apply it here? Yes. 0 and XORed with 0. How many ones do you have here? Do you have even number ones or odd number ones? You have even number ones because you have 0. 0 is an even number. So the XOR is 0. Here you have only 1, means it's an odd or even, it's an odd number. So I have 1. Here also odd, only 1. Here I have even number of ones because I have 2 ones. So if I apply this here, I can get an F in just a shortcut or a hack. Simply count the number of ones in the inputs. So you have here 0, 0, 0. Is this even or odd number? The number of ones here is 0, means I have even number of ones. Right, what about this combination? Odd number of ones. Let's just say, put them a number of ones in the inputs. So here I have 0 ones. Okay, here I have 1, here I have 1, here I have 2, here 1, here 2, here 2, here 3. Now you can build a relationship between the odd and even ones and the output F. Okay, so this is even, so F is 0. This is odd, F is 1. Odd, F is 1. Even, F is 0. Odd, 1. Even, 0. Even, 0. Odd, 1. So I can drive the truth table for the F or for the 3 variables XOR without going into too many steps. Right. What if I want to write the equation for F in SOP or POS? This is a problem here because actually I have to use the TT again in order to get the equation. Okay, so F can be written as sum of mean terms or product of max terms. And sum of mean terms, I can actually circle those ones here. I have actually 4 ones. Okay, so if I'm about to write F as sum of mean terms, so I can simply write F as the summation of, this is the designator 1, yeah, it is the sum of 1, 2, location of ones, 0, 1, 2, 4, and 7. If I'm about to implement this, this will be a huge circuit. It's a circuit that has 4 AND gates and 1 OR gate, and these 4 AND gates, each of them has 3 inputs. Very big circuit. All of this big circuit can be simply implemented using this 3-input XOR gate. If I know this information of the XOR. So whenever you have this scenario at your output, if you ever get an output that you need, that you have this odd number of ones in the inputs, okay, that means you can use the XOR gate directly. Let's go back. So why we are just putting the SOM? Can't we simplify the XOR into a minimum sum of minterms other than the sum of minterms? Okay, so in order to do that, we need to build the K-map. And we build the K-map for 3 variables. The answer is yes. But let's try to build the K-map and see what will happen. This is a 3-variable K-map. Inputs are x bar x, y bar y, z bar z bar. Okay, designators 0, 1, 3, 2, 4, 5, 7, 6. Great. Now, what are the midterms of the function? I have midterm at 1, 2, 4, and 7. And the rest are the location of zeros. Now, do whatever you want. Try to simplify the XOR into minimum or smaller equation other than the sum of minterms. You cannot, because unlikely or unfortunately, okay, each one on the K-map is surrounded with zeros from all directions. So each one on the K-map should be taken alone. There is no simplification for the XOR other than this. So 2 formats to the XOR, and similarly for the XNOR. It's either you represent it as it is, 1 gate, 1 tau delay with the 3 inputs, and you definitely win. Or you go to the sum of minterm representation, means a huge circuit of 5 different gates, 4 AND gates, 1 OR gate, and big circuit. Each of them has 3 inputs, okay, in order to implement for you the XOR. XOR is a very useful circuit, as we will see, inshallah, in the next lecture when we start lecture number 17, or lecture number not 17, 18, when we go and discuss the different circuits of chapter 4. We will learn how important and how useful the XOR. Whenever you have a scenario like this, you are definitely go directly to the XOR if there is no simplification that you want to do. If there is a simplification, you have to extract, no way, you have to extract an XOR to its basic sum of minterms or product of max term, and actually solve the problem from the basic definition of the sum of minterms and product to max terms, the canonical representations of the Boolean function equations. At this stage, we finish all of the material for lecture number 13 and all the material for chapter 3. We are done with chapter 3, and inshallah, we will start chapter 4, lecture 17 in our next video session. We have at least 1 to 2 tutorials for chapter, I think 1 tutorial will be enough. Inshallah, either me or the TA will inshallah give you the tutorial. We'll also post or upload the video for the tutorial of chapter 3, so you can learn more examples for the K-map, for the other gates like NANDs and NORs, multi-level NAND, 2-level NAND. I want you to come to the class, inshallah, prepared. You have to watch the videos. You have to try your best to solve the problems from the homework that's already posted. So when you come to the tutorial or come to the online session for the class, you are prepared, you have questions, because we will not repeat the material. We will just I will open an open discussion and questions and answers. I'm willing to solve anything on the board for you. I'm willing to give you more examples, but this is due to your need and due to your requests. Thank you.